All right, so our other video today, actually our second one, is on thermochemical equations. And thermochemical equations are just where we have heat in the equation. So we've had equations, lots of chemical equations before, where we just balance the equations, and so we had our mole ratios, but now we're going to add heat in. So let's get started with that. So with the thermochemical equation, we have an example here of 2 moles of water is going to be decomposed into 2 moles of hydrogen gas and 1 mole of oxygen gas. Now, it's called a thermochemical equation because it has heat in it, the equation. So the heat of this reaction is 572 kilojoules. It's positive. So that means that heat has to be put in. So to decompose 2 moles of water into its elements, we're putting in 572 kilojoules. I could also, instead of writing it at the end here as positive, I could write it on the reactant side because I have to add in 572 kilojoules of heat to make this reaction happen. If I flip the equation, then that will change the sign of the delta H. So now flipping it, the H2, 2 moles of H2 plus 1 mole of O2 goes to 2 moles of water. Now it's a negative 572 kilojoules because flipping the equation is now exactly the reverse. The H2 plus O2 is making water, whereas up here, I was breaking apart the water into H2 and O2. So now heat is a product because it's negative. So negative delta H or writing heat in as a product. We don't usually do both. Okay, so it's one or the other. So if it's written at the end and it's positive, we know it's endothermic, heat is a reactant. If it's written at the end and it's negative, we know that's an exothermic reaction, and we could write it in as a product, or we can write it at the end as negative, either or. So this is saying to make 2 moles of water from its elements, we have 572 kilojoules of heat given off. So though that heat can be used with the mole amounts as a ratio. So it doesn't matter, I could use anything in the equation and compare it to the heat. So I could say 2 moles of H2 is equal to that much heat, or 1 mole of O2 is equal to that much heat, or 2 moles of H2O is equal to that much heat for this particular equation. Okay, and we're going to do some calculations with that. So the size of the delta H depends on how much of the substance is reacting. It is related. If I have 2 moles of H2, 1 mole of that, and 2 moles of that, that's how much heat is given off. If I multiply or divide the reaction by any number, I also have to do the same thing to the delta H. So if I multiply all of these by 1/2, which is the same thing as dividing each of these by 2, I have to do the same thing to the H value. So now the second equation is dividing everything by 2, so that I now have only 1 mole of H2 reacting with 1/2 mole of O2 to give 1 mole of H2O. And then when I divide the delta H value by 2, I can see that it is going to now only give off 286 kilojoules, okay, because I cut the amount in half, so only half the amount of heat is given off. For this reaction, if this is all I was shown, Al2O3 plus 1,676 kilojoules makes 2 moles of Al plus 3/2 mole of O2. I can see that since the heat is on the reactant side, I know the reaction is endothermic. I could also have written the delta H at the end here as positive 1,676 kilojoules. Okay, so it's usually either or. The heat's written in the equation on the reactant side if it's endothermic, or at the end as a positive value, or if it's exothermic, it would be written on the product side or at the end with a negative value. And once again, I can now use that delta H value as a conversion factor with the mole ratios. So here's an sample problem. Here's my balanced equation. I will have Al2O3 going to 2 moles of Al plus 3/2 mole of O2, and my delta H value is 1,676 kilojoules. My question is, how many grams of aluminum can be formed when 1,000 kilojoules of heat is used? So I'm given amount of energy. That's what I'm going to start with. And my conversion factor, my mole to heat ratio or heat to mole ratio, comes from this equation here. It shows me, I want to go to aluminum. So for 2 moles of aluminum, there's this much heat. Okay, so starting in kilojoules, I have my ratio now to get from kilojoules to moles. Okay, and I get that from the balanced equation. This much heat to 2 moles of aluminum. I could go to any of these things, but it's asking me for grams of aluminum, so that's what I want to go to. So kilojoules to moles of aluminum, and now to get to grams, I use molar mass, and then I can look up the molar mass of aluminum, which is 27, and now I can just multiply and divide. Molar mass. So 1,000 times 2 divided by 1,676 times 27 will give me 32.2 grams of aluminum. Okay, and that is my answer. Okay. Let's try another one. For the reaction of mercury 2 oxide decomposing into mercury and oxygen. So again, I need my balanced equation. 2 moles of HGO goes to 2 moles of Hg plus a mole of O2. And the heat is positive 182 kilojoules. So I know that that much heat has to be put in to make this happen. And this question then is, how many kilojoules are needed to react 25 grams of mercury 2 oxide? So now I'm starting with my 25 grams of mercury 2 oxide. I need the molar mass of that to get to moles. Always have to go to moles. Remember, mole is the goal. So I divide by the molar mass to get to moles. And now my mole to heat ratio, there's 2 moles of HGO to 182 kilojoules. And so then my grams cancel, my moles of HGO cancel, and I'm in kilojoules, and my answer is 10.5 kilojoules. Okay, so in both cases, whatever's given, that's what I start with. And then in this case, I was in kilojoules first, so kilojoules had to go on the bottom that I got from my balanced equation. I went to whatever it asked me to go to, in this case, aluminum. So there's 2 moles of aluminum in the balanced equation. And then I used molar mass to get to grams. The second problem was exactly backwards. I was starting in grams of my substance. I used molar mass to get to moles of that substance. And then I used my mole to heat ratio from the balanced equation to get to kilojoules. Okay, so really it's just like our stoichiometry problems from before. We're just adding in a mole to heat ratio. There's different types of enthalpy. We could have heat of combustion. If we're looking at burning something, we could measure how much heat was given off when it was burned. If we're mixing together an acid and base, we could have heat of neutralization. We've already done the problems with the heating curves where we had heat of vaporization and heat of fusion, how much heat it takes to melt 1 mole of a substance or how much heat it takes to vaporize 1 mole of a substance. These are all just delta H values. So again, those are just heat values per 1 mole that we can use as conversion factors.